Hi, welcome back. In this lecture, I want to give you the basic intuition of Shor algorithm, and I'm going to focus on the quantum aspects of the algorithm. So how to use quantum computing to solve the Shor algorithm. In the previous lecture, we saw that we can solve an equivalent problem, or the original problem we want to solve, which is to factorize an integer number into prime number by solving an equivalent problem that consists of calculating the repeat period Rp of a special function. This special function is calculating as the following. We take a co-prime number a, in this case 2. We take the power to x, that is our variable number, and then we take the modular operation with the integer number we want to calculate the prime factor. We saw a very brute force, naive approach to calculate this repeat period. What we do, we just plot in the function of x, the function, and then we check after how many iterations a certain value is repeating. So on the left part of this slide, you see a plot of 2.x mod 15, where 15 is the integer number we want to calculate the factorization. And you see that after 4 iterations, a number is actually repeating. And therefore, the repeat period is 4. We saw also in the past the usage of the discrete Fourier transform, and we saw it in connection or calculating the period or a frequency of a function. And therefore, we can try to think to use it also to calculate the repeat period in the case of the Shor algorithm. And that's the basic intuition of using quantum approach to calculate the repeat period. So what we're going to do is to calculate the DFT. We are going to use the quantum version of DFT, the so-called quantum Fourier transform, on a set of quantum state in a superposition on which we encoded this special function that we have here, 2.x mod 15. The QFT will implement the discrete Fourier transform and will leave our output QPU register in a superposition of different frequency contained in the input, which is our special function here. So for instance, we do a measurement of this signal that has been encoded in the quantum state. We're going to get the correct frequency that is here 4. And also notice that we're going to get 4 equally spaced peak. So not only the frequency correct here, but also we're going to find 4 peaks. So in the case of factoring 15, we calculated our function to the x mod 15. Then we applied DFT and we find 4 equally spaced and together also with the correct frequency of 4. From this then we can easily calculate the integer number using the GCT algorithm. So let's see the example in this case of factoring 35, and the 2 to the x mod 35 is slightly different from the previous example of factorizing 15. In this case, the repeat period is 12. We saw that this function repeats after 12 iteration. So the repeat period of a to the x mod n in this case is 12. And one thing that we also notice that there are also 12 evenly spaced highest weighted spikes. So if we perform the DFT, so we can check 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So for a pattern with the repeat period p, the magnitude of the Fourier transform will have exactly p evenly spaced spikes. And we're going to use these results to calculate the repeat period using the QFT. As I said, the number of spikes is just equal to the repeat period. So we will need some technique to perform the DFT. In our case, will be the QFT because we are working in the quantum regime. And then the next step will be to calculate how many spikes we have in the output of the QFT. So since the spikes are evenly spaced and we know the size of our register, we can estimate how many spikes there were in the QFT. And this number of peaks is the same as the repeat period of our input signal. So let's look at the general structure of our Shor algorithm, the quantum version. The first part is to initialize the parameters. The most important aspect is the number that we want to factorize, in this case E15. We're going to also to set the number of precision bit, and also we're going to set the coprime, that is a prime number, typically is chosen as a simple one, such as 2. And then the results will be the output of a function that we call the Shor, that takes as input the integer number we want to factorize, the precision bits, and the so-called coprime. So let's look now more deeply the Shor function. So the Shor function is the following here. We have this function consists of different two main parts. A quantum part that is called Shor QPU. So we are going to run the Shor algorithms on the QPU, and the output of this QPU Shor algorithm will be the calculation of the repeat period. This is the quantum part. The Shor algorithm has also a classical part that consists of calculating the GCD, given as an input the repeat period and the coprime. So this is, just to summarize, the main function we have it here consists of two parts. One to calculate the repeat period using the quantum computing part, and then one classical part that is called Shor logic, that is taking the repeat period and calculates the prime number P and Q. And this part is based on the GCD calculation and is done on the classical part. You see, this is the classical part that is using the two GCD factor. So to summarize, there are three basic steps that we are going to use in the Shor function. The first will be to create a superposition of quantum states, and then we are going to calculate in parallel using this superposition the function of a to the x mod n. So we will need to do this using some quantum arithmetics. Go first in superposition, do the quantum arithmetics. After that, we're going to apply the QFT in order to calculate the number of peaks. So to learn the repeat period P. After that, as a final step, we will take the repeat period we calculated with the quantum computer, and we use a conventional CPU algorithm based on the GCD algorithm to calculate our prime factors. This is the last slide of this lecture, and talk to you soon.